So welcome to part 2 of vector algebra for physics. So from the last video, we saw the absolute basics that's required for us to understand about vectors and their various properties. So from this video onwards, we're going to get into the technical aspects of what a vector is and how to represent a vector and various things to do with vectors. So starting off with a basic question, what is a vector? So in physics, generally there are two types of quantities. So the first quantity is called a scalar quantity, and the second type of quantity is known as a vector quantity. Okay, so there is a scalar quantity and a vector quantity. So in scientific terms, a scalar quantity is any quantity which has only magnitude, but a vector quantity is a quantity which has both magnitude and direction. Okay, so this is the basics, like in the scientific terms. I'm going to illustrate the difference between the scalar quantity and a vector quantity using an example. So now let's say we have a person. Okay, we have a person who's moving at 5 kilometers per hour. Okay, he's moving at the speed of 5 kilometers per hour. So now the scalar quantity, whenever I say any quantity to be scalar, the scalar part basically means the number part or the quantity part which can be measured. So scalar in general means a measurable quantity. When I say 5 cups of milk or 4 donuts, that 5 and 4 happens to be the scalar part. So the scalar part is basically the measured number or measured amount of anything. So over here, this guy is moving at the speed of 5 kilometers per hour. So the scalar part is basically the measured amount of his speed. So the scalar part over here happens to be the 5 kilometers per hour because that is the magnitude. Magnitude basically again means the number or the quantity that is measured. So this, the 5 kilometers per hour is the scalar part. So now if I ask you guys a question, where will this person be after 2 hours? So now we know that this person is traveling 5 kilometers in 1 hour. So he is traveling 5 kilometers in 1 hour. So in 2 hours, he'll obviously travel 10 kilometers. So now if I were to ask you, tell me the final position of this man, it would be an illogical question because this person can move in any direction with the speed of 5 kilometers per hour. And until and unless I specify which direction is traveling along, you can't tell me the final position. So now this is where a vector quantity comes in handy. So vector quantity, as I said, is a quantity which has both magnitude and direction. Okay, so the magnitude part, as we saw, is the 5 kilometers per hour. So now if I tell you this person is moving along this arrow, okay, along the positive x-axis like this at the speed. So the vector part is the quantity which tells you this man is moving with a speed of 5 kilometers per hour along this direction. So now this part as a whole is called a vector because this quantity has not only the magnitude but also specifies the direction in which the person is propagating in or moving along. But a scalar part is only this part, only the number part, which is the quantity that is measured. Okay, so now that we've learned on what a vector quantity basically is, I'm gonna start off by continuing a topic that I stopped from the first part of the video. So I'm gonna resume by drawing the 3 axes about whom we discussed in the first video. So let these be the 3 axes. So now this of course is the x-axis, this of course is the y-axis, and this of course is the z-axis which is pointing towards you. Okay, so now if I were to tell you this point over here on the x-axis at a distance of 1 square unit. So this term square unit is basically that 1 centimeter part in your graph paper, or 1 square unit is basically a unit whose magnitude is 1 or whose length is 1. Okay, it can be meter, it can be centimeter, it can be anything. But in this case, we're just going to call them square units to avoid confusion. Because in the last video, if you remember, this person traveled 5 meters along x, 6 meters along y, and 15 centimeters along z. So when we represent the triplet like the last video, we would have to say 5 meters, comma 6 meters, comma 15 centimeters. So now as you can see, there's a mismatch in the units, and this might give us further problems in the future. So to prevent this mismatch in the units, we don't specify the units at all. We just say the numbers, and it's understood the unit happens to be a square unit or anything that has magnitude only 1. So now what I'm going to do, I'm going to draw a line. Consider this line to be along the x-axis, stopping exactly at this point. Okay, and now I'm going to draw one more line along the y-axis. So this blue line is the line along the y-axis, whose magnitude also happens to be 1 square unit. The magnitude basically means the length of this vector is also 1 again. And I'm going to draw one last line along the z-axis. This green line is a line along the z-axis, whose magnitude also happens to be 1 square unit. Okay, so now I have basically 3 lines, the 3 colored lines along the 3 different axes, each whose magnitude is 1 or length is 1 square unit. So now in vectors, using these 3 basic vectors, we can represent any other quantity or any other vector. Now why am I calling these 3 lines to be vectors? All these 3 lines happen to carry the magnitude part, which is basically their length part, and they also happen to carry the direction, because these arrows, as you can see, this is pointing towards x, this arrow is pointing towards y, this arrow is pointing towards z. So all these 3 lines, they carry the magnitude part and the direction part, so they happen to be vectors. So that is the whole point of me referring to these 3 lines to be vectors. So now these 3 lines in physics have a special term. So now these 3 lines are called unit vectors. So now this is pretty self-explanatory. The unit part means their magnitude happens to be 1. So there are 3 vectors whose magnitude happens to be 1, and they are along the 3 respective axes. So these 3 vectors are called the unit vectors. And using these 3 unit vectors, we will be representing any other vector in the 3-dimensional plane. So like we saw in the last video, in this triplet over here, the first term happens to be the distance along the x, the second term distance along the y, and the third term the distance along the z axis, correct? So what we're gonna do, instead of drawing this brackets and comma every single time, we're gonna skip drawing the brackets and the commas, and we're gonna move on to a different type of notation. So we're gonna have 3 alphabets, okay? So namely I, J, and K. So now these are 3 alphabets. So now look at this red line over here. So this red line is a line along the x-axis whose magnitude happens to be 1 unit. Okay. So now we are going to represent, as I said, these 3 lines are special lines because they're called unit vectors. So I'm going to represent this red line, or I'm going to give it a special name. I'm going to call this red line I cap. So this cap part basically tells this I is a vector. Okay, now for now, just bear with me over here when I say I cap. Let's just assume that's a name given to the red line. And similarly, the name given to this blue line happens to be J cap. And finally, the name given to this green line happens to be K cap. Okay, now these 3 are the names of the respective lines. So I cap, J cap, and K cap. So I cap, J cap, and K cap are the names of these 3 lines or these 3 unit vectors. So now what I'm trying to do over here is this I cap, correct? So whenever you have this term I cap, it tells you that that line is pointing towards the x. So for example, if I say there's a vector which says 2 I cap. So now this is a vector, correct? Because whenever there's a cap, it becomes a vector. Let's assume it to be like that. So when I say 2 I cap is a vector, how would you plot it, or how would the vector look like? It would be a vector. Let me draw it in a different page. So again, the 3 axes. Okay, so now when I say a vector called 2 I cap, we know that I cap vector is basically a vector over here along the x-axis whose magnitude happens to be 1 unit or 1 square unit. So when I say 2 I cap, all that we have to do is draw one more I cap such that the magnitude of this also happens to be 1 unit. So in total, this vector is a longer line with twice the length of I cap. So if you see what I'm trying to tell over here, whenever I say this vector over here 2 I cap, this 2 part is basically the scalar part, correct? And I cap part is basically the direction part. So like I told you in the previous page, when I told you the line along the x is an I, the line along y is a j cap, and the line along k is a k cap. These are 3 unit vectors. So over here this 2 part is basically the scalar part, and the I cap part tells you that this vector is along the x-axis. So like the last part 1 video where we would mention 2, over here we said 2 I cap. So 2 I cap, what does it tell us? 2 tells us the length of the line is 2 units, and I cap tells us it's along the x-axis. And similarly, if I were to go, let's say 3 units above the x-axis, y-axis over here, if this happened to be 3 units, not drawn to scale of course, if this line along the y-axis happened to be of length 3 units, how would I represent this vector? So the scalar part happens to be 3. Now it's along the y-axis. So I put a j cap along with it. So this is the scalar part or magnitude or length of the line, and this j cap is basically telling you that it is along y. So one last example along the z axis. Let's say I were only to travel half a meter or half unit. I were to travel half unit along the z axis. Now how would I represent this vector? The scalar part is 1/2 and the direction is along the z axis. So it happens to be k cap. So if you observe keenly over here, this I, j, k, they are basically unit vectors or lines with magnitude 1 unit along the respective axis. So we just multiply them with any number that we want and we get a new vector. If I multiply I cap, which is basically the small one line like I showed you in the last page, so I cap is basically this line. If I multiply that by 2, I get a vector that is twice its length but along the same axis. Let's say I want a vector that's half its length. So I say half I cap. So I get a vector which is half the length of I cap along this axis. So I cap basically is a unit vector. So unit vector has magnitude 1 and carries only direction along with it. It carries the data of direction. Like k cap carries the data that the vector is along z. J cap carries the data like the vector is along y. So with these 3 vectors, we just multiply random numbers to them and we happen to get different vectors along the respective axis. So now this is the basic way in which we represent vectors in physics. So now let's take a complicated case and see how to represent that vector. Okay, so now let me draw our coordinate axis as usual again. Don't mind the point of coincidence, not drawn to scale of course. So x, y, z. So now that we're getting a little more specific, let me also mention the negative x, the negative y, and the negative z. So these 3, what do these basically mean? This is 0, this is 1, 2, 3. From here there will be -1, -2, -3. Similarly 1, 2, 3, -1, -2, -3. So 1, 2, 3, -1, -2, -3. So that's the negative x, y, z axis respectively. Okay, so now we're going to take a simple example. So there's a man, let's assume there is a man at the origin, at the point of coincidence of the 3 lines. So this person moves 14 units along the positive x-axis. Okay, and then he moves 5 units along the negative z-axis, and then he moves 7 units along the positive y-axis, and finally he moves 3 units along the negative x-axis. Now finally he's at some point P, I'm not going to mark the point P because it will look uncertain. I'm going to mark it in a little more while. But finally, let's assume he's at a point P. Okay, let's say anywhere over here, not that accurate, but a point P. So now what I want you to find is I want you to find the vector OP. Assume the origin to be O and the point is P. I basically want you to find the formula or the representation of the vector OP. Okay. So now we're going to split this into the respective parts. So I'm going to use the red color marker for the X part. So first of all, he travels 14 units along positive X. So we know that the unit vector along X is I cap. So now this carries direction alone. So now we want a vector that's 14 times in length of this one. So we just multiply it by 14. So 14 I cap is its position after a while when he travels along X. So he travels along X, and finally when he is at 14 square units away, this line, and I have this vector over here, this vector is basically 14 I cap. That is his first part. From here he goes 5 units in the negative Z direction, or he travels in a way like that, parallel to the negative Z axis. He travels like that for 5 units. So now we know a unit vector along the positive Z axis happens to be K cap. So now a unit vector along the negative Z will be minus K cap. So this minus does not signify the vector has -1 magnitude. Magnitude can never be negative. Magnitude is basically a quantity that's measured. It has to be 1 or 2 or 3. You can't have -1 liters of milk, correct? So this -1 is not the magnitude. The minus part basically represents the direction. It says it's opposite in direction to your regular direction, because K cap will be along positive Z, minus K is along negative Z. So that's what this minus sign represents. The magnitude of this vector is again 1 unit only. Don't get confused. So the direction is minus K. But now since he's traveling 5, we're just going to multiply 5. Okay, so now this is the second part of his motion. So the final part of his motion over here, the penultimate part of his portion is 7 units along positive Y. So then he's traveling, actually from this point, he's traveling 7 units in the positive Y direction. Correct? So now once he travels 7 units in the positive Y direction, we know the unit vector along Y happens to be J. Positive Y is J cap. So now since the displacement or the magnitude of traveling is 7, we just multiply this unit vector by 7. So now this vector gives us a vector that has length 7 times J cap, or the unit vector. Okay. So the final part of his motion is 3 units along negative X. So we know unit vector along X is I. So unit vector along negative X will be minus I cap, correct? Now he is traveling 3 units. So we just have to multiply this by 3. Okay. So now we have the individual components of his motion given to us. Okay. So now we have to represent this vector as a whole. So let's say from here, I forgot to mention that properly. So from here, let's say he travels some distance over here, let's say 3 units, and comes to this point. Okay, this is this final part, 3 units along negative X. So like I said, don't assume this to be point P, assume this to be point P, and we basically are calculating this vector over here. This is the final vector, because like I said, it wasn't right of me to plot this vector. So he first moves 14 units along X, 5 units along negative Z, 7 units along Y, 3 units along negative X. So finally his position is somewhere over here. So now what I basically did was I plotted, or I joined that line with the origin. So now this line is the OP. So this is the final displacement part, or the final displacement line, or the final displacement vector. Why am I calling it a vector? It has some magnitude, which we will learn to measure very soon, because this line, the length of this line can be measured using the length of these 3-4 respective lines. So this line happens to have some magnitude, which is basically the length of this, correct? And it happens to have some direction. See the arrow? It's pointing like that in some weird way. Just because it's weird doesn't mean it has no direction. It still has direction, but it's not explicitly along X, Y, or Z. It's a combination of all of them, which we'll see after we represent the vector. So this line has a magnitude. It's pointing to something, which means it has some direction, so it's a vector. Okay. So now, like I said, we got the individual components of motion. So now, how do we finally represent the vector? We just add all these values. It's as simple as that. So over here, when I have 14i, I say 14i, this minus sign, it can be it can come out, you can represent this as minus 5k, there's a 7j, so you have plus 7j, and finally you have a minus 3i. So one final warning, this minus 5 is not the magnitude. Magnitude, as I said, can never be negative. You cannot have negative 1 liters of milk, right? So this minus 5 is not the magnitude. 5 is the magnitude. The negative sign just represents the direction is opposite to the original kind of displacement or the original kind of direction. So in vectors in general, whenever I say negative, it is never the magnitude. The negative sign represents the opposite direction to your original direction. Okay. So now this is the final vector. So over here we have 14i minus 3i. This is basically equivalent to 14 minus 3, which is 11. So the final vector is 11i cap plus 7j cap minus 5k cap. So this is the final vector. So what is this basically telling us? Like we saw in the first part, we saw how much a person moves along x, along y, along z. Then we plotted a triplet. So similarly over here, this value basically tells us there's a person at the point of coincidence or the origin. He moves 11 units along the positive x, 7 units along the positive y, and 5 units along the negative z. Okay. So we basically reduced this 11, 7, minus 5, which is a weird entity, to something that is noticeable and something that's quite clear. 11i cap plus 7j cap minus 5k cap. So if you guys still can't grasp the concept of unit vectors and what I, j, k exactly mean, just replay this video once again. Go back to the part where I explain what I, j, k caps are respectively are, and then you will have certain amount of idea on what these are. If you still happen to have any more doubts, do leave them in the comment section and I'll get back to you as soon as possible regarding your doubts. So now this was the basics on a vector. So now this line that we have over here is called OP. So we say OP. So OP is basically what? OP is a line. So how do we represent a vector? We just say bar. Okay. So OP without this line on top is called a bar. Okay. That's how we call it. So OP is a line. But when I say OP bar, it becomes a vector. So this OP is a line which will have only the length of the line OP, or this will contain only the scalar part. But the moment I say bar, OP bar, it will have the scalar part, which means it will have the magnitude, it will have the length along with direction. This arrow comes into place. So it becomes a vector. So we say OP bar equals this one, or this thing that we got. So OP bar is 11i cap plus 7j cap minus 5k cap. So this was quite a long video for this concept actually. This one is one of the most easiest concepts in physics, vectors and their notation. But this happens to be the basics for a lot of lessons in physics. So if you grasp these basics of vectors very well, the further concepts that the further lessons that we're gonna see in physics will become a cakewalk, especially when you get into mechanics and motion in 1D and 2D planes. We'll be talking so much vectors, we'll be talking so much I, J, K continuously. So make sure you understand these very basics very well, because these lay the foundation for the entire Newtonian mechanics in physics that we're going to cover, which are in the syllabi of your high school. So yeah, that's it for part 2 of vectors, on how to represent a vector and what a vector actually is. So in the further videos, we're going to be looking at a few more properties of vectors. So yeah, that's it for this video guys. If you enjoyed the video, do leave a like. If you found it useful, do subscribe. And if you have any doubts whatsoever, no matter how trivial they might be, don't hesitate to leave them in the comment section below, where I'll try to get back to you as soon as possible. Thank you.